On the morning of January 11th, 1994, a man named Ed Weiler drove to work in the dark. He had done this hundreds of times before. The streets of Baltimore were quiet at that hour. The sky still that particular shade of pre-dawn gray that doesn't quite commit to either night or morning. He parked, walked across a nearly empty lot, and pushed through the glass doors of the Space Telescope Science Institute, carrying a paper cup of coffee he had picked up at a gas station down the street. The cup was cheap. The lid was the kind that dents if you grip it too hard. He set it on the corner of a desk near the main hallway, meaning to come back for it. He would not come back for it for hours. By the time he did, it would be cold, and he would not notice, because the thing he had just seen on a monitor in a back room had rearranged his understanding of what was possible that morning. This is the story of that image, that room, and what it cost to arrive at it. To understand the weight of January 11th, you have to go back 3 years, or really 24 years, because the story starts there, in the mid-1960s, when a Hungarian-American astronomer named Lyman Spitzer began arguing with institutional patients that humanity needed a telescope in space, above the atmosphere, above the turbulence and humidity and light pollution that had limited every ground-based observatory in history. A telescope that could see the universe as it actually was. The proposal moved through NASA bureaucracies for years. Studies were commissioned, canceled, recommissioned. Mirrors were spec'd and respec'd. The price estimates climbed. By the time congressional funding was finally secured in 1977, the project had absorbed nearly a decade of planning and the professional energy of hundreds of scientists and engineers across multiple institutions and contractor facilities. By the time the primary mirror, 2.4 meters across, ground from ultra-low expansion glass with a surface accuracy measured in nanometers, was completed and certified in the mid-1980s, more than 10,000 people had contributed to the program. The launch, originally planned for 1983, had slipped to 1986, then been delayed again by the Challenger disaster, then finally arrived on April 24th, 1990, when the shuttle Discovery carried Hubble to orbit on a mission watched by millions of people around the world who had grown up knowing this telescope was coming. The joy lasted 6 weeks. When the first science images came back in late June, the astronomers waiting for them felt something shift inside their chests that they struggled afterward to describe accurately. The images were blurry, not the ordinary blurriness of an instrument that needed tuning. A specific, precise, diagnosable blurriness caused by a flaw in the primary mirror that had been ground with extraordinary skill in exactly the wrong profile. The error was 1.3 micrometers, less than 1/50th the width of a human hair. The engineers who built the mirror had been so skilled that they had made it perfectly wrong. The resulting spherical aberration meant that light reflecting off the outer edges of the mirror focused at a slightly different point than light reflecting off the center, and the resulting images were smeared into soft halos around every star and galaxy, with roughly 85% of the light falling outside the intended focal point. $2 billion, 24 years of development, the most advanced optical instrument in human history, and it could not focus. The congressional hearings were brutal. The late-night comedy monologues ran for weeks. NASA's administrator testified under conditions that could charitably be described as hostile. The engineers and scientists who had devoted years of their careers to Hubble went to work in institutions where, for a time, strangers in elevators asked if they were embarrassed. The damage to institutional credibility was severe enough that several subsequent NASA programs, the Mars Observer, the Wide Field Infrared Explorer, faced additional scrutiny they would not otherwise have faced, specifically because of Hubble. Ed Weiler, serving as Hubble's chief scientist at NASA headquarters, spent the next 3 years doing two things simultaneously: defending the telescope's continued scientific value to skeptical administrators in Congress, and working with a team of optical engineers on the solution. The solution was called COSTAR, Corrective Optics, Space Telescope Axial Replacement. The concept was, at its core, elegant. If you know the exact shape of the error in a mirror, you can design a compensating optical element that introduces an equal and opposite error, canceling the first. The execution was something else entirely. The corrective optics had to fit within the existing instrument bay dimensions. They had to be installable by astronauts wearing pressurized gloves in the vacuum of space. While Hubble orbited at 28,000 kilometers per hour, they had to perform with tolerances measured in nanometers. The servicing mission, STS-61, aboard the Shuttle Endeavour, launched in December of 1993. Over 11 days and 5 spacewalks totaling 35 hours and 28 minutes outside the vehicle, 7 astronauts performed what was effectively microsurgery on a spacecraft the size of a school bus, replacing instruments, installing COSTAR, and repairing hardware that had been in orbit for 3.5 years. When Endeavour landed on December 13th, the mission was called an unqualified success, but no one had seen the images yet. The Space Telescope Science Institute in January of 1994 was a building that smelled like fluorescent light and coffee and warm electronics. The monitors in the main analysis areas were the large, heavy cathode ray type. Deep gray bezels around screens that flickered very slightly in a way you only noticed once you'd been staring at them for 6 or 7 hours. The analysts and astronomers who worked there dressed the way academic scientists dressed in that period: chinos, flannel shirts, fleece vests that were simultaneously practical and somehow timeless. They communicated by telephone, by memo, and by walking down the hall and leaning in a doorway. There were no smartphones to check, and the primary connection to the outside world was a fax machine and a workstation terminal connected to the early internet, which in January of 1994 still looked mostly like text. The processing team had been working through the night, not because of heroics, because astronomical data processing simply took that long in that era. The images from Hubble arrived as raw data, streams of photon counts from the WFP-C2 camera, the new wide field and planetary camera that had been installed during the servicing mission, with corrective optics built directly into its relay lenses. Raw data was not an image, it was numbers. The process of transforming those numbers into a calibrated, artifact-corrected, scientifically valid image required running the data through multiple pipeline stages, correcting for known detector artifacts, unsubtracting dark frames and bias frames, applying flat field corrections, and finally assembling the calibrated array into something a human eye could parse. The target chosen for the first corrected images was a galaxy cluster designated Hubble 2218. The choice was deliberate and methodical. Hubble 2218 was a known quantity. Its structure had been catalogued by previous instruments, its redshift measured, its position precisely known. It was a complex target with bright elliptical galaxies at its center and fainter background objects at its periphery, which meant it would reveal Hubble's corrected performance across a wide range of brightness and angular scales simultaneously. It was not chosen for beauty. It was chosen as a diagnostic. The processing ran. The pipeline ran. The team waited with the specific quality of alertness that comes from too much coffee and not enough sleep, but an inability to actually feel tired because the adrenaline of proximity to something important overrides the fatigue signal. At some point in the early hours of January 11th, the final calibrated image appeared on a monitor. The people in that room had looked at thousands of astronomical images. They knew what Hubble produced before the correction: the soft, halo-smeared blobs that had become an embarrassing symbol. They knew what the best ground-based telescopes could show, even through adaptive optic systems. They had spent months calculating what the COSTAR correction should theoretically produce, modeling the expected point spread function, for running simulations of what the corrected images would look like given the precise error profile of the original mirror. The calculation said it should be extraordinary. The calculation was correct, but the calculation had not prepared them for the experience of seeing it. The image was not just sharper than the uncorrected Hubble. It was categorically different in the way that a window is categorically different from a wall. Where the uncorrected instrument had shown a smear of undifferentiated brightness around the central galaxies of the cluster, the corrected image showed individual objects, dozens of them, each with distinct structure and resolved morphology. Elliptical galaxies with visible color gradients from core to halo. Spiral galaxies seen edge-on and face-on, and running through the image at multiple positions, and the long curved arcs that are among the most visually striking phenomena in observational cosmology. Gravitational lensing arcs, produced when the enormous mass of the cluster bends the light from more distant background galaxies into stretched, distorted curves, exactly as Einstein's general relativity predicts. Objects that had been completely invisible in the noise of the uncorrected images simply existed now, present and resolved, and ancient. Their light having traveled toward Earth for billions of years to land on a detector on a satellite at precisely this moment. The sharpness matched the theoretical diffraction limit of the optics, not approximately, not within acceptable margins, exactly, which meant the corrective optics were performing as well as physics permitted. The instrument had been fixed, and it had been fixed to perfection. Ed Weiler stood in front of the monitor for a long time and said nothing. Multiple people who were present have confirmed this. Other people came in. Someone said, in words approximately like these, "It worked." The statement was so inadequate to what they were looking at that it produced a brief, strange quiet. Then more people came in, and the quiet broke, and the morning changed. The paper cup of coffee on the desk down the hall was cold. Ed Weiler did not notice for hours. What Hubble showed humanity over the years that followed is by now part of the permanent inventory of human knowledge. Within 2 years of the correction, the team produced the Hubble Deep Field, a single long exposure image of a patch of sky that appeared completely empty through every previous instrument, revealed to contain nearly 3,000 individual galaxies, each one a system of hundreds of billions of stars, each one so distant that the light captured in that image had been traveling for between 1 billion and 13 billion years. Scientists spent weeks recalibrating their intuitions against an image that showed, in practical visual terms, that the observable universe contained something on the order of 2 trillion galaxies. Data from Hubble's corrected instruments contributed directly to the 1998 discovery that the expansion of the universe is not slowing down, it is accelerating. The force responsible for that acceleration, which no one had predicted and no one fully understands today, was named dark energy. The scientists who confirmed it were awarded the Nobel Prize in Physics in 2011, and their primary observational tool was Hubble. The telescope also provided the first direct observational confirmation that supermassive black holes, objects containing millions or billions of times the mass of the Sun, sit at the centers of essentially every large galaxy, including our own. It allowed precise measurement of the Hubble constant across distances that had previously been inaccessible. It imaged the atmosphere of a planet beyond our solar system for the first time. None of this was visible on the morning of January 11, 1994. What was visible was an image on a monitor, a cluster of galaxies with structure that had been invisible the week before, and a group of people in a fluorescent-lit room in Baltimore who had spent 3 years fixing a mistake. Not their mistake, but a mistake they had decided was theirs to fix anyway, and were now standing in the quiet aftermath of having done it. There is a particular quality to that specific kind of silence, the silence that comes after years of work encounter a moment of verification. It is not triumphant. It is not relieved exactly, though relief is somewhere in it. It is something more like recognition, the feeling of having been right about something for a very long time, and discovering that the universe agrees. The Hubble Space Telescope has now produced more than 1,600,000 observations. It has been cited in over 20,000 scientific papers. Its images have appeared on the walls of schools on every inhabited continent, defining for an entire generation the visual language of deep space, the spiral structures, the gravitational arcs, the pillars of gas and dust that are the nurseries of new stars. When people today close their eyes and picture a galaxy, they are usually picturing something Hubble showed them. All of that is the legacy. But the legacy began in a moment that was just a cup of cold coffee and a monitor in a quiet room at the end of a very long night, and a few people who had decided that the error could be corrected and had turned out to be right. We live in an age where the James Webb Space Telescope now shows us the universe in infrared light at distances and depths that Hubble cannot reach. The technology moves forward, as technology does. The story of Hubble will eventually be history, in the way that all extraordinary things become history, familiar, referenced, slightly abstract. But I keep returning to that morning, not to the Nobel Prizes or the deep fields or the confirmed equations, to the cold coffee, to the silence in a room before anyone knew how to describe what they were seeing. What does it mean that 10,000 people can build something flawed, and then another group of people can choose to fix it, can design the fix, build the fix, launch the fix into orbit on a shuttle, install it with gloved hands in the vacuum of space, and bring it back home working perfectly? What is the actual ceiling when we decide something matters enough to be worth that? If you're still thinking about that question, I'd love for you to be here for the next one. Subscribe, and we'll keep asking it together.
Oh, before you go, if this video made sense to you, subscribe to the channel. This helps YouTube deliver this content to even more people. Also, leave your like. It's essential for our growth here on the platform. And if you want to support us even more, super thanks is right below and helps directly with the production of new content. Comment here where you're from. And thank you for watching us until the end. See you in the next video.